Good day everyone, Mr. Cargill here with our next AutoCAD video, and for this video we're going to be looking at CAMS. Now CAMS, it's an important topic in technical drawing, whether you study building or mechanical drawing. It's mostly used in mechanical drawing, but you're expected to understand the principles of CAMS, whether you do building or mechanical drawing. And this is a topic in BMed and not really that much in technical drawing. There are CAMS in technical drawing as well, but it's mostly in BMed. Now it says a CAM can be defined as a mechanism which is designed to make a part of a machine move in a particular way. It says, for example, CAMs are used to open and close valves which control the petrol mixture going into the exhaust gases and coming out of an internal combustion engine. So basically what a CAM does is to change the motion of something. So for example here, so this is a CAM and this is what we call a follower. Alright, so the CAM is spinning, it's rotating, and as the CAM is rotating, it causes this follower to go up and come back down. So it's changing rotary motion, alright, or rotating motion to linear motion, alright, so because the follower is just going up and down. So that's what the CAM does. It changes the direction of something, alright, and it changes like rotary motion to linear motion. So in other words, a CAM and follower is a device which can convert rotary motion, which is circular motion, into linear or reciprocating motion. Alright, good. So it says, how does it work? It says, therefore the valves must open at the right time and at the right speed, and it is the CAM that determines this. The control on the valve is exercised by the profile of the CAM, determining how the follower lifts and falls. Alright, so the CAM is what determines how the follower lifts and falls. And for the follower right here, we have different types of followers. We have a flat follower, a knife point follower, and you can see that the edge is shaped like a knife. This is a flat follower because this edge is flat. We also have a roller follower because this part rolls, and an offset follower which is kind of slant. Alright, good. So it says, what are some other applications of CAMs? It's used in machines, a lot of machinery, whether it be paper cutting machines or spinning and weaving textile machines. Also used in like automatic lathes and so on. Alright, so it's used a lot in machines. Now, it says types of lift and falls of a CAM. The three examples of the different types of lift and fall are uniform velocity, simple harmonic motion, and uniform acceleration and retardation. So what do we mean by types of lifts and falls? When the CAM is spinning or rotating, alright, and it's making one complete revolution, if we are to plot the movement of the CAM and how the CAM behaves during one complete revolution, alright, that would be our performance diagram, and our performance diagram will show how the CAM rotates. So it rises and falls, and it rises and falls in different ways. Some of those ways include uniform velocity, simple harmonic motion, and uniform acceleration and retardation. So today we're going to do a drawing, on uniform velocity. So the drawing that we're going to look at today is going to be a drawing of a CAM that has that moves in such a way that the performance diagram will have a uniform velocity. And we'll look at the performance diagram, what it means, how it works, and everything. But before we do that, we need to look at the different types of lifts and falls. Alright, so right here we have uniform velocity. And uniform velocity works like this. It just goes up and then comes back down like that. So uniform velocity, it doesn't have to come back down. Over here, this could change from, when it's coming back down here, it could change from uniform velocity to simple harmonic motion, or uniform acceleration and retardation, or a mix between the two. Alright, but this is uniform velocity. It just goes up uniformly like that. Alright, so the drawing that we're going to look at is going to have is going to involve uniform velocity. So this over here now is the drawing that we're going to look at. This drawing right here. And it says here that these are the specifications that we are given in this. We're not given this is the performance curve or the performance diagram. So we'll need to draw this, and we'll need to draw the CAM. But we won't be given this we won't be given the CAM here, and we won't be given the performance diagram. For this question, all we're given is the specification, and we're supposed to use the specification to draw the CAM and the performance diagram. All right, so here it says that the shaft diameter is 15 millimeters. So the shaft is this part here, this part, and right here it says shaft diameter. Well, again, you wouldn't have the drawing, so you wouldn't be able to see that. No, our next thing with the CAM is this. You will see the way that the CAM is rotating. There will be an arrow that shows you whether it's rotating in a clockwise direction or an anti-clockwise direction. So in this case, this arrow is showing us that this CAM is rotating in an anti-clockwise direction. Why is this important? This is important because that will tell us how we are supposed to number the different parts after we divide up the CAM. So in this case, we're numbering it in an anti-clockwise way. All right, so we start here. So this is 12, but it could be 12 and 0. It will be the same points. So the next point is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. So we number it in an anti-clockwise direction. Because the arrow shows us that the CAM is moving in an anti-clockwise direction. All right, good. So we have the specification. So the shaft diameter is 15 millimeters, and the minimum diameter is 30 millimeters. Now the question might be asked, why is this called the minimum diameter if this diameter here for the shaft is smaller than the minimum diameter? This is called the minimum diameter because, as you can see, this is the CAM, and this is the point on the CAM right here that actually touches this circle here. All right, so this circle is called the minimum diameter because, let's say, from the center of the CAM to this point here, that's the shortest distance to the CAM. All right, let's say you're in the center of the CAM here, or there's something in the center of the CAM, and it needs to get to the edge of any edge of the CAM. The shortest way to get to that edge is to travel from here to here. All right, so that's the shortest diameter. So that's the minimum diameter. Good. So that's why it's called the minimum diameter. So now we can start our drawing because we have the shaft information and the minimum diameter information. So let's head over to AutoCAD and start our drawing. So the shaft diameter is 15 millimeters. So I'll just select a circle, just choose a place to start, and the diameter is 15. In this case, I'm using the radius. So let me do this. Since it's 15 and I'm using the radius, let me just set my units to 0.0. Yeah, good. So I'm going to use a radius, and the radius is going to be 7.5. Yeah, 7.5, which is half of 15. Good. And then the next radius, the next diameter is 30. So this radius is going to be 15. All right, nice. So now what I have here is this: my shaft diameter and my minimum diameter. So the next thing I need now is the lift. So it says that the lift is 15 millimeters, all right? And then this is the performance diagram over here. So before we get any of this, before we get anything over here, this is what I'm going to do. I'm going to divide my circle into a number of equal parts. 12 works well, all right? So I normally divide my circles into 12 equal parts. Good. So I'm going to divide this into 12 equal parts, divide up the CAM, the minimum diameter and the shaft diameter into 12 equal parts. So let's do that. So here now, I'll do this by doing this. I'll just draw, let me turn on ortho. All right, so I'll draw a line like that. And let me extend this down. I'm just extending it down because I want my points to be outside of the CAM. I want it to be touching the CAM. So that's why I'm extending them out like that. So like here, like here. You see these lines that divide up the minimum diameter and the shaft diameter, they go outside because we need them to touch the CAM. So that's what I'm doing here. So that's why I'm extending them out by so much. All right. So let's go back to AutoCAD. I'm just extend this out even a bit more. Again, no specific measurement, just extend it out. All right, good. So then I'll select a line, and from the center here, I'm just extend this line out again, like that, measurement, and then I can just extend it on this side as well, no specific measurement, just about long enough. That should work. So now what I'm going to do is to divide this into 12 by using the array command. So I'll just click on the lines and I'll type array, and I'll select array polar. Good. And I'll click right here in the center, and then now that divides up my circle into 12 equal parts. Awesome. So now that I have this divided up into 12, I can now number my different parts. All right. So I'm going to select text. I'll just click the drop down arrow on text, and I select a multi-line text. Good. And now my text, my first text right here. All right. And this point is going to be 12. This point is 12 and 0. So you could label it 12, or you could label it 0, or you could label it 12, 0. Either way works. It's 12 and 0. All right. So let's, for now, I'll just keep it at 12, and I'm gonna just change the color so that the text can have a different color. So I'll change it to something bright, maybe like yellow. All right. So let me just move this from here. Sorry, let me just move this. Turn off ortho, turn off object snap, and I'll just move it down a bit closer to the drawing. So like here. So now I'm just going to copy this 12 here. I'm going to copy it, bring it to the different parts, the different lines, and then I'm going to number the different lines. Let me just bring it out a bit like this. I'm not really placing them at any specific points. So I'm just gonna do this, and then now I will put in the correct values. All right. So this is 12, which means that this is 1 here, and so on. All right. So that means that the next point is 2, and then we just label them like that, going across. Again, if you know of a simpler way to do numbering, like a faster, quicker way to do numbering, just let me know in the comment sections below, because numbering is the only thing that takes more time on AutoCAD than it would if I was doing this on paper. All right, so if you know a quicker way to do numbering, just please share in the comment section below. All right, 6, so this is 7. And just label all the way back to 11. Yeah, because 0 and 12 will be the same points. So we'll just label all the way back to 11. So this is 9, 10, and 11. Nice. All right, so we have this. So the next thing we're going to do is this. We are going to draw the performance diagram. And to draw the performance diagram, this is what we're going to do. I'm going to draw a line. All right, I'm going to draw a line from here, from this point. I'm going to turn on back object snap, turn on ortho. I'm going to draw a line from the top of the circle here, from this quadrant. I'm going to bring it all the way across here. Right now, I'm not bringing it across by any specific measurement. All right, so I do that, and then I just choose a place to start. So let's say I start like somewhere on the line, like right here. Good. Let me just turn on some of the different things here in object snap. I need to turn on midpoint, geometric center. I normally just have everything on in object snap, unless I need to turn off something. So I just normally just keep everything on. All right, so I'll choose a place to start. So I could start anywhere outside of the drawing. So I could start like right here. And it says that the lift, all right, here it says that the lift is 15. So that means that this line that I'm going to draw is going to be 15 millimeters. 15, like that. Now, here we had divided the circles into 12. So we're going to need to divide this line here into 12. So what I'm going to do is just to trim this for now. I'll just trim this part. All right, I just trimmed off that part. I'll draw it back, but I just trimmed it so I can divide this. So I'm going to divide this into 12 equal parts here. All right, and what I normally do is this. Let me delete this line. So what I've done is this. Right, this line would come from here all the way over here. Right, so the edge of this line, the base of this vertical line needs to be in line with the top of this circle here. All right, so like that. So from here, I'm going to draw a line, and this line, the line can be any measurement. Just ensure that it's divided into 12 equal parts. But I normally just make the line 120. So when I divide it into 12, I get like 10 segments of 10 millimeters, but it doesn't have to be exactly 120. So I'll do this. I'll divide this into 120. Actually, I won't divide it into 120. This is what I'll do. I will make the performance diagram, the line here, I'm going to make it equal to the circumference of the circle. All right. So the circumference of this circle would be, this circumference is pi r square, or 2 pi d, and this circle here has a radius of 15. So the diameter is 30. All right. So if I am to do this now, let me go to the calculator here in AutoCAD. So the circumference would be pi times the diameter. So that's 3.14, or actually I can use pi here, times the diameter, which is 30. And that equals 94.2. All right. So 94.2. So from here, I'll draw this line, 94.2. 94.2. Good. And then I'll bring this up 15, and then bring this across like that. Good. So now I have this. All right. And what that represents is this right here, this part here. Okay. Awesome. So now this is what I'm going to do. I am going to divide this into 12. So I'll do that by typing divide. So I'll type divide, and then I'll just click on the line here, and it says enter the number of segments. I want 12 segments. It's divided into 12, but it's not showing. So when it's not showing, just type DDP. All right. Click on DDP type here, and you can select any one of these division points that anything that you want to divide the line. I'll use this one. And the point size, I figure out that 2 works well. If you choose 2 and it's too small, you can choose a bigger number or something, but 2, this is 2, it works well. So yeah. So what I'll do is also just copy this line here. So I'll copy this. All right, let me close this. So I'll copy that line and just bring it to the different division points. So I'll copy it from here, bring it to here, and all the different division points. Like that. Perfect. Now, it says that for this is how it moves. So let's look at the rest of the information. It says that the performance, it goes up like that for 90 degrees. All right, so what this presents here, so let me number this before I continue. So in the image, it's numbered like 0, 1, 2, 3, and so on and so forth, but I'm going to number it like this. I'm going to number it differently. I'm going to number it in terms of the different degrees. All right, so let me copy this. Turn off object snap, turn off ortho, and I'll just bring it to the different points. So like there, here, all the different points. Alright. Well, actually, I'll number it 1 to 12, but I'll explain what it means. So the first point here is, let's call this 0. Alright, it calls it 12 right here, as it has 12, but 12 and 0 again would be the same point, so I'll just call it 0. Alright, and we'll just number this going all the way to 12. Good, and once we get this now, we can finish drawing the performance diagram, and then use the performance diagram now to complete the drawing of the CAM. Alright, I'll do this video on as uniform velocity. I'll do one that has simple harmonic motion, and do one that has uniform acceleration and retardation, so that we can get an understanding of CAMS and how they work. But I'll put those in separate videos. Alright, also, if there's anybody who has been watching this video and you're interested in like tutoring session for CXC or for CXC or CAPE, it doesn't have to be just for BMed or technical drawing, but for any subject. I'm going to post a link in the description below that will have information on company that can offer tutoring for any CAPE or CXC subject that you might be interested in, and you can check that out. All right, good. So we have that. So once we have that now, over here it says that this moves like this. This is the performance. It says 90-degree uniform velocity to max lift. All right, 90 degrees. So right here, this is divided into 12. All right, and each of these divisions represent 30 degrees. All right, so if we were to number this using degrees, we start at this point. So this is 0, 30 degrees, 60, 90, so on and so forth. All right, which means that this would be 0, 30, 60, 90, so on and so forth, going all the way to 360. Good. So it says performance 90-degree uniform velocity to max lift to the maximum height here. So from here it goes up to the 90-degree point, and again, if we're using degrees here, this would be 0, 30 degrees, 60 degrees, 90 degrees. Each division point goes up by the next 30 degrees. So this is 30, 60, 90. So from here, this goes up to 90 degrees, then it dwells for 180 degrees, and then it goes down for 90 degrees. Dwells just means it stays in the same place. So that's like this. From here, all right, let me turn on back object snap, turn on back object snap. So from here, this goes across and it goes up to 90 degrees, which is here. Good. And let me just use a different color for this. Let me change the color here. Let's use red maybe. Actually, let's use something brighter. Yeah. All right, and then now, so it goes up to 90 degrees and then it dwells for 180 degrees. All right, so it dwells for 180 degrees. So if it dwells for 180 degrees, this is what, 30, 60, 90, 120, 150, 180. So right here, and then it falls for the next 90 degrees. All right, so that's the performance diagram here. So it goes up, comes across, and then it comes back down like that. Goes up for 90, dwells, which means stays in the same place for 180 degrees, and then falls for 90 degrees. So that's what we have here. All right, that's what's happening here. So now we see some horizontal lines coming across to this line from 12. How do we get those horizontal lines? This is how you get those horizontal lines. When we draw this line here that represents the linear velocity motion, this line will intersect these vertical lines at different points. So where they intersect the vertical lines, where this diagonal line or this slant line intersects these vertical lines, we just draw horizontal lines from those points. All right, so here now, let me use like a construction line for this, like a gray or so. All right, so from here now, so this vertical line cuts this diagonal line right here. So we're going to bring this across. Let me turn on ortho all the way to line 12 right here. All right, and then this line, this point, you know, comes across and it comes here. So I drew that line from where this diagonal line met this vertical line, so right at the point. Perfect. So now I'm going to bring this across from this edge here right at the top and bring it across to this line on line 12 here. Okay, so we have that. So that's perfect. Let me just make this one of the construction lines as well, so I understand a little bit better. So that would be there, and this would line up perfectly with the 0 here. All right, so all these points, we bring them across. So now we can finish the drawing of the cam. All right, because over here, as you can see, it says the rotation is anti-clockwise, we know that. So when we bring across these lines, this is how we're going to get the cam. All right, like this. I'll just use use an arc. You could use a circle, but I think I can use an arc as well. I can use an arc, and I can use start, center, end. Actually, no, I'll just use a circle. So from here now, this is the center of my circle. And this here, all right, I'm going to draw the circle from the center of the cam to where this first horizontal line meets this line right here at point 12, this vertical line at point 12, all right? That line at 12, so from the center, where this horizontal line meets this vertical line here at line 12. I don't want to draw one from this point because this circle is already there, the minimum diameter. That circle that represents the minimum diameter is already there, so I don't need to draw a next circle from there. So now I'll do the same thing again from here. I'll draw a circle to where the next horizontal line that comes across meets line 12, which is right here. And from here now, from this center, I'll draw that circle to where this circle meets this horizontal line right here. And we basically would have completed our cam. So now we just need to plot it. And I'm going to plot it by using a spline. All right. So I'll just select spline, S-P-L-I-N-E. I select a spline. I'll start here, because that's the first point. I'm going to turn off ortho. No, our second point. Where's our second point? Over here, this is line 1, right? This is vertical line 1. It meets the diagonal line and it comes across to this point. Good. And then it comes over and it cuts this line from this line 1 here. All right. So this is line 1 over here. So this is vertical line 1. It meets the diagonal line here, across to point 12, and then this circle comes down and meets that, cuts this line 1 right here. So this is our next point. So from 0 to 1 right there. Good. So we'll continue. This is line 2. It goes up to right here, comes across to here, and then this comes over and cuts this line 2 right there. Good. The next one is line 3. All right. So this circle comes across, goes all the way around, and it cuts this line 3 right here. So now here's the dual period. It remains the same all the way to 9, to line 9 right here. So what that means is we'll keep on marking the points on this circle for 4, 5, 6, 7, 8, and 9. All right. And again, the reason for that is because this here is the dual period. So dual means it remains the same for all of this. So from 3 to 9, it remains the same. So from 3 on that circle, it remains the same all the way to 9. And then it starts to fall. So it starts to fall at 10. So this is the line from 10. All right, the vertical line from 10. It meets the diagonal line right here. So I bring this line across now. That line meets point 12 here. And then it comes across, comes around here. And it cuts line 10 right at this point. So that's my next point. Good. And then the next one is line 11. So line 11, it goes up, meets the diagonal line right here, comes across here, and then it cuts, it comes across here, and then this circle comes around here and cuts the line from 11 right here. And then our final point is point 12. So we just bring it back to where we started, press spacebar, and there you have your cam. All right. So that's your cam, and that's your performance diagram with the information that you are given. All right. So this is how you would go about representing a cam or drawing a cam. All right, using simple linear velocity. All right. And to clean this up, I could just move up like my different numberings a bit closer. I don't think I put them too far. So yeah, that's just let your drawing look a bit better. Just bring up your numbers and closer to the edge of the drawing
and so on and so forth. Yeah, but that's how you go about completing a CAM like this, given those specifications. All right, so in the next video we're going to look at how we go about drawing a CAM when we using simple harmonic motion, and we'll also look at how we go about drawing a CAM using uniform acceleration and retardation. All right, good. So I hope you found this video helpful. If you did, please drop a like, and a subscription would be nice, you know. All right, and you can also turn on your bell for so that you can be notified whenever I release new videos. All right, so thanks for watching, and do have yourselves a fantastic day.